Hello, this is Jacob, and in this video we're going to be talking about the solution of discrete state space equations. In the previous video we were talking about the solutions of continuous time state space equations, and in state space you pretty much can, for every continuous time system result, there's a discrete time equivalent, and I think it makes the most sense to just learn those as you go, because they're so similar to the continuous time equivalent. So we're going to talk about this discrete system, and sometimes you call these discrete time systems rather than continuous time, but also sometimes you just call them discrete because time isn't really a critical notion here. So we're talking about systems that look like this, where we have some state, and that state is evaluated at some sample k, and instead of evolving xy looking at x dot, a time derivative, we just look at the next sample, so at sample k plus 1, and we say that's going to equal some a matrix times a to the k, a at sample k I should say, plus some b matrix times u at sample k, and then we're going to be looking at y at sample k is some linear combination of our states at sample k plus our inputs at sample k. So this is the discrete time system or discrete system. X and u are the state and input at sample k. X at k plus 1 is the state at the next sample. X of k is not evolving continuously, but rather in these discrete finite steps. And the solution to solve for how x of k evolves, and I can say how x of k evolves in time, but that doesn't really make sense. It really just means evolves from sample to sample, is pretty explicit. I mean, if we start with some initial condition, you can say, if I want to figure out what my state is at sample 1, that's just equal to a times my state at sample 0 plus b times my input at sample 0. It's very straightforward to compute like this. The x at sample 2 is going to be defined really similarly, and so you can think of these as being sort of nested, right? Where the solution for x at 2 is a function of x at 1 and u at 1. But the solution x at 1 was already solved here. So really the solution x at 2 is a times a x at 0 plus b u at 0 plus b u at 1. And so if you work that out, you see that's equal to a squared x at 0 plus a b u at 0 plus b u at 1. And if you were to repeat this process over and over, you would get a general equation for x at k, which is equal to a to the kth power times our initial condition, x at 0, plus this summation. And the summation is going to be from index m equals 0 to up to k minus 1. And it's going to be a raised to the power of k minus 1 minus m times the d matrix times u at index m. And so just like with the continuous time systems, we can think of this as a natural response, and this thing as the forced response, which is the forced response, again, just like with continuous time, is a not very clean thing. It's kind of ugly, but it's counted for the fact that u can be completely arbitrary inputs. And so if u can be kind of crazy, then its forced response can be kind of crazy. The natural response, on the other hand, looks very similar to the natural response of the continuous time system. And if you remember how the continuous time system it looks something like this. The solution was x at t is equal to e to the at times x naught. And so for continuous time systems, this matrix, e to the at, which a is an n by n thing, and so e to the at is also an n by n thing. That was the really important matrix in the time domain solutions of these equations. Well, in discrete systems, this a to the kth power, which is also an n by n matrix, is going to be the really important thing that we're going to keep track of. Now, we have this matrix A, this n by n matrix A, and so A is still similar to Jordan form because these concepts of Jordan form are just matrix properties. They have nothing to do with linear systems of equations at all. They're just properties of square matrices. So A is still similar to a Jordan matrix. And so if I raise A to the k power, that's just nothing more than qj q inverse times qj q inverse times dot dot dot. And at each instance, the q and the q inverse are going to be next to each other, and those are just the identity matrix. And then this q inverse and this q will be an identity, and they're all going to collapse away. And when you're done, what's left with is a single q times j to the kth power times q inverse. So the solution for A to the k is something that's relatively easy for us. We can figure out its Jordan form, qj q inverse, then raise the Jordan form to the k power, and then as the last step, just pre and post multiply by q and q inverse. So then the question is, what is j to the k? This whole method of quickly computing a to the k is based on being able to quickly compute j to the k. Now with continuous time systems, we learned that if we want to compute e to the at, that might be complicated in general, that e to the jt is actually something that we can compute and sort of memorize the pattern and then use that over and over. Well, it turns out computing j to the k, if j is a Jordan form matrix, is also something that's really straightforward. So if I make a Jordan block that looks like this, and I'm going to do the 4x4 case again. I did the 4x4 case with continuous time, and it's enough that you can fully see what the pattern is, so you can generalize it to 5th, 6th, 7th order matrices, and also collapse it down even as small as 1 degree of freedom matrices. So let's consider a Jordan form like this. So it's got lambda on the diagonals, it's got 1s on the super diagonals, and 0 everywhere else. So 4x4 Jordan form, a Jordan block. Well, if you do this matrix multiplication explicitly, a pattern will emerge, and you'll see that j to the k looks like lambda to the k on all the diagonals. And I should start writing these spread out more because these other terms start getting really big. So lambda k on the diagonals, and then k lambda to the k minus 1 on the super diagonals. And then the next term here is k times k minus 1 times lambda to the k minus 2 all over 2 factorial. And that is here as well. K times k minus 1 times lambda to the k minus 2 over 2 factorial. And it's pretty easy at this point to figure out what the pattern is. And so you say, well, this is going to be k times k minus 1 times k minus 2 times lambda to the k minus 3 all over 3 factorial in this spot. So this pattern holds, and if you have a 2x2 Jordan block and you raise it to the k power, it would just be this here. If you had a 3x3 Jordan block, it would just be this here. So this idea of kind of seeing how the pattern evolves lets you solve these in general. Now, Recall that the reason why we're learning these discrete systems is we're ultimately interested in modeling systems that evolve in these discrete steps, or at least systems that can sort of be easily modeled that way, even if it's not a perfect description of reality. And so some of the types of systems that you can model this way are economic systems and financial systems, things that we're going to calculate this year's money based on last year's amounts and interest rates, and also things like population models. We're going to look at how many people there are based on how many people there were last year and how many are going to be born and die in any given year. So these are the kind of systems we're going to be interested in for discrete state-space equations. There's another class of systems which are actually continuous time systems that are being controlled by a digital computer, and so the computer can only sample those continuous time systems in discrete instances, and we call those systems that are really continuous systems but sampled discretely as sample data systems, and there will be a separate video on sample data systems.